Now that we've talked about resistance and where it comes from on the microscopic level, we're going to connect resistance to the other circuit quantities that we've been looking at, current and potential difference. So, we're going to say that resistors in this class almost always follow something known as Ohm's law, which states that the current through a resistor is directly proportional to the potential difference applied. And it should make sense that this proportionality constant is 1 divided by resistance, because if you have more and more resistance in your circuit, you're going to have less and less current. So also, it's very common to see Ohm's law written as delta V equals IR. I know that we'll use it like this a whole bunch, but I like to write it as I equals delta V over R, as does the equation sheet, because in your circuits, it's really rare that you can't really have devices that control the current as easy. But what we can do is we can totally change the battery voltage. So, just to show causality, usually we would like to say that potential difference causes a current. This is very similar to saying that Newton's second law is A equals F over M versus F equals ma. I know they're the same, but you don't usually get to pick your acceleration. You usually get to pick the force that's applied. So this is why we usually write it like this. There's nothing wrong with delta V equals IR. We certainly use it a lot. But that's just to show why it looks like this. So if we get a linear relationship out of current and potential difference, then the material follows Ohm's law, and we call it ohmic. And if we graph this, notice we get y equals 1 over r times delta v. So we'd get a linear relationship with slope not r, but 1 over r. If we graph this. If you graph the other version, you get a slope of r, which is going to be more convenient. Ohm's law isn't necessarily true for all materials. So if it's not true for a material, you just call the material non-ohmic. We will assume that any resistor we encounter follows Ohm's law, unless if it's the objective of the problem to test if it does or not, where you're looking for this linearity. So let's show some graphs here. We want to sketch I versus delta V for a low resistance bulb, a high resistance bulb, and a non-ohmic bulb. So first we'll just start. So let's think about what it means to have, well, what any of these curves should do. So we know that delta V is sort of your height change or your energy change. It's going to be proportional to the sort of push that these charge carriers are going to experience. So regardless of what shape we're going to have, we know that it's going to be at least like a positive correlation. So let's think about what's going to happen if we have low resistance. So if you have low resistance, this means that for a given potential difference, you're going to get a lot of current. So we're going to have a steep slope. So this is actually our low resistance bulb because you get a lot of current. Conversely, we'll get rid of the double arrowhead. If you have a high resistance bulb, you're going to get a low amount of current. So notice that the low resistance bulb gets a lot more current for a given potential difference. So this is our low R, this is our high R. So non-ohmic, what would non-ohmic look like? Well, it just has to be nonlinear. Now, if you're curious, if you actually do this for a light bulb, most light bulbs are actually going to generate a curve that looks more or less like this before they burn out. So you actually keep bumping up the voltage, bumping up the voltage, bumping up the voltage, and you're just not getting the same increase in current that you were before. And if you want to think about why, it's actually because as this light bulb filament heats up, its resistance increases. That's a physical reason why we get this shape. This is the classic lab. Calculate resistance using Ohm's law. Group of students investigate Ohm's law using a variable power source and a resistor of unknown resistance R. Draw this circuit using standard notation. So it doesn't matter, it's a variable power source. We'll still call it a battery. And there's our resistor. So, of course, since we always like to practice our potential color coding, if this is our circuit, notice that whatever potential difference is applied to the applied from the power source, it's going to be dropped across the resistor. So the supply shows both the applied voltage and resulting current. So there's some sort of LED display on this battery power source that's showing both of these things. So this is why we often use a different symbol for delta V, right? It seems kind of weird that we get delta V measured in V. So we'll talk about, usually we call this like a capital epsilon just to avoid confusion with the unit, but indicate a pair of quantities that could be graphed to produce a straight line usable for finding resistance. We should know it. Ohm's law says that these two quantities are going to be proportional. So let's actually figure out what we want to graph. So I'll show you, it doesn't matter what order you graph in. This is how we stated Ohm's law. But realize if we graph this, it's slightly annoying because we get this 1 over r denominator as our slope. And we can actually solve the problem a lot quicker if instead we write it as delta V equals I times r. It always helps during this process to understand what the variables are. So delta V is a variable, I is a variable, r is a constant. So we can just rearrange this as delta V equals r times I. So I is a variable, delta V is a variable, and r is a constant, so that is our slope. So you could have done it the other way, and you'll get a reciprocated slope. No big deal. But if you graph delta V versus I, you get a slope of r. So yeah, we like that because the slope is just equal to r. And if you can ever do one of these best fit line questions without having to do a bunch of algebra with your slope, it's probably a good idea. So, as per usual, insert my typical line of mining off camera. We graphed our delta V in volts. We graphed our current in amps, linear scale. Best fit line, half above, half below. Then we do it in Desmos, and Desmos gives us our regression equation. And this is a really easy calculation for the resistance R, because we said that R was actually just the slope, which is equal to 7.5. The rise of our graph was actually volts, and the run was current, so it was amps. So I said last time that we'd discover how the ohm relates to other circuit quantities. So an ohm is actually a volt per amp. But 7.5 ohms would be our resistance. So an ohm tells you the voltage drop you get through a resistor for every amp of current put through it. So when batteries were first invented, lots of spelling errors here. The driving force of current flow was described as electromotive force, which we call an EMF. So before we knew the concept of voltage, it was referred to as electromotive force, or EMF. So they thought it was this force. It is really the electric force. What's driving this process is energy or potential. So just like we said, they guessed wrong on which way current goes and its convention. Also, we'll just use this term EMF interchangeably with voltage. So we'll use this epsilon symbol interchangeably with a voltage or a potential difference. And it also just helps us manage the units better, so we're not saying delta V is measured in volts. So we get this weird, this strange looking table here. So there is no difference between this concept of EMF and what we've been calling a voltage. So now what we can do is we can actually talk about the rate at which energy is being transferred. Now, if it's a battery, this would be the input rate, and if it's a resistor, this would be the output rate, or the rate at which energy is being dissipated as heat. So there's actually 3 equivalent power formulas. The first one is the definition. Power is equal to the current times the potential difference. But if your material follows Ohm's law, you can get rid of V or I by doing a substitution and get a relationship in terms of one of the two, delta V or I, that incorporates resistance in there. So we get I squared R, or we get delta V squared over R. I like this one. This one is, I call it the not centripetal acceleration, because for mechanics, acceleration in a circle is V squared over R. So we call this the not centripetal acceleration formula. So power is not energy. Remember, power is the rate that you use energy. So this is measured in watts, which tells you how many joules are being used every second, how many joules are being transferred every second. So if you want to find energy dissipated, you have to multiply by the time that a given component is active. So power is joules per second, but energy is just joules. So be careful about which one you want. So let's do some deriving here. So using the definition, we want to verify that this is a reasonable expression for power. So we're claiming that power is equal to I delta V. So I is measured in amps. Okay, that's not helpful, because if I multiply these together, I get amps times volts. I have no idea what that is. But we do know that I is the rate of charge flow. So we get coulombs per second. And what is a volt? Well, a volt was how many joules it takes to separate each coulomb of charge. So if we do that, notice the coulombs actually cancel. So we are just left with joules per second, which is energy per time, and that's equal to a watt, as expected. And now by applying Ohm's law, we want to verify the 2 other expressions. So we can start with power equals I delta V. This is the formula sheet one, which is the definition. But often this is actually the least useful, because it's rare we'd know I and delta V. Usually you'll know resistance. So we're going to substitute away for these. So first, what we could do is, first we could use the fact that we'll go in order with the formulas. Let's say first you want to use the substitution delta V equals IR. So if you do that, you can write power is equal to I times delta V, which is IR. So we get I times IR, which is I squared R. So there's one of them. Cool. What if instead you wanted to do the other substitution? Because we said that actually our preferred definition of Ohm's law says that I is delta V divided by R. So we can say that power is equal to I, which is delta V over R, times delta V. So we see that the delta V's combine in the numerator, and we get power is equal to not centripetal acceleration, delta V squared over R. So we actually get quadratic dependence. So it's kind of misleading to say that power, like for ratio reasons, it can be misleading just to look at I delta V. Because what people forget, as we'll see in this next problem, is these don't get to live on their own islands. Because Ohm's law says that these 2 quantities depend on each other. So that's actually what we're going to look at. A resistor is connected to 2 different power sources. With a battery that has EMF epsilon, or voltage, right? The resistor power dissipation is P1. And if you double that battery EMF, the power dissipation is P2. So here's a very reasonable argument, it seems. Power equals current times voltage. That's true. Doubling voltage doubles power, so P2 is double the original. Well, this is apparently incorrect, so let's see why. So yes, it is true that power is current times voltage. But what the student forgot is that current depends on voltage. So these are actually linked. You can't double one of these without doubling the other. So what really happens is, yes, you double the voltage, but doubling the voltage also doubles the current by Ohm's law. So they missed an extra 2. So doubling voltage does double power via P equals IV. Like, that is totally true. But due to Ohm's law, current and voltage are related. So doubling voltage also doubles the current, resulting in a 4x increase. And how could you see that more directly? Well, we could see that more directly by cutting out by actually cutting out the current. Because we're just talking about power and voltage, and it's the same resistance, so we should use that. So we actually know that power can be written as delta V squared over R. So my new power can be found by squaring my voltage, doubling. So my power goes up by 2 squared in the numerator, and it's the same resistance, so nothing changes there. So this tells us that P2 is 4 times P1. So this is a very common mistake, is to not realize that voltage and current are linked and just blindly applying this formula. So that's why this is usually the least useful, because it's rare that you know those things. You often know either the voltages in the resistance or the currents. But all three are useful and are totally worth memorizing, or at least being able to derive. All right. Battery of EMF epsilon is connected to a cylindrical resistor with area A, length L, resistivity rho. First, we want to find current through the cylinder. So, well, I want current. What is current? Current is delta V over R by Ohm's law. Okay, but I don't have R. I have all this geometry stuff. I have the area, I have the length, and I have the resistivity. So we have to remember from last time that resistance is resistivity times length over area. So we're just substituting into this. So the delta V is just our battery EMF epsilon, and our resistance is rho L over A. So we have a double denominator, as I call it. So if you have a double denominator, you can swing that to the numerator. So we get epsilon times A divided by rho times L. All right, now we want power dissipated by the resistor. We can pick literally any of the three expressions. Power dissipated by the resistor. So here we have a current. We already solved for current. And we know the voltage. So here's a case where it's kind of rare that you know voltage and current, but we do. So maybe let's just use the definition. Our current was epsilon A over rho L. Our delta V was just epsilon. So we just pick up a square. So we get epsilon squared A over rho times L. And notice you could kind of see this however you wanted. That if you didn't actually have to calculate the current first, you might just say instead, to do it without finding current, you would say power is equal to delta V squared over R. Delta V is our battery voltage of epsilon, and R is rho L over A. So once again, we get the double denominator, so that A swings up to the numerator, and we get epsilon squared times A over rho times L. And we get our expected result. So you could actually do this without finding current if you use the third power formula. Suppose the resistor is replaced by a wider cylinder of the same material and same length. So we're increasing area. So what do we think about the battery's power output? Increase, decrease, or remain the same? So power is the rate that this battery is transferring energy. So if there's more charge carriers being put into the circuit, then there's going to be a higher power input / output. So what does a wider cylinder do? Well, if you have a wider cylinder, that's going to decrease your resistance. And if you decrease your resistance, you get more current flow. So battery power output increases. So without referencing equations, how can we prove this? Increasing area decreases resistance. If there's less resistance in the circuit, the current increases. So if you output more current or more charge per second at the same energy per charge requirement, you get more energy per second, right? Because voltage, that's your energy per charge. So if it's the same energy per charge, but you're pumping out more charges every second, there's a higher rate of energy transfer. Now, it's actually really easy if you look at your expression from part B. So in part B, we actually found that the power is equal to EMF squared times area divided by resistivity times length. So why does a wider cylinder have a larger power output? Well, we see that power is proportional to area. So this means as A increases, power increases as expected. Gotta include the as expected, right? And there is a subtlety here. The power dissipated by the resistor has to be the same as the power input by the battery because of energy conservation. So energy in from the battery equals energy out to the resistor, because that energy's got to go somewhere. It doesn't just vanish. So energy in equals energy out. So you have to use that subtlety. All right. So that's everything we can do kind of just with one resistor. But of course, why not combine them? So today's concept is going to involve something known as REQ, or equivalent resistance. So any resistor network actually has a single resistor that will model it, that'll get you the correct current. So this is a made-up mathematical object that behaves the same way. So to find REQ for a circuit, you have to divide the battery EMF by the total current from the battery. So this is really just applying Ohm's law to the whole circuit. And usually what we'll do when we're finding current is we use this variation of Ohm's law that says I total is equal to the total voltage, epsilon, divided by the total resistance, REQ. And we should be careful about calling this total resistance because depending on the setup, it's usually not add them all up. So I'm calling it an equivalent resistance and not a total. Okay. So we'll cover this later in our last section on circuits, but we're going to just introduce the rules first, and then we will prove them a bit later. So this tells us that no matter what your circuit looks like to start, there's always some mathematical way to combine them into a single resistor. And that's helpful because then you can just do Ohm's law to find the current. So the whole point of REQ is it tells you how much current your battery pumps out. So we use all these rules for combining resistors just to get the current. So to begin, we have the easy case of equivalent resistance, which is series. So series, you just add the resistances together. So the only time you can add resistance to find REQ is if your resistors are connected directly in series, meaning there is no path that you can take other than going through one after the other. So if I go through resistor 1, I'm forced through resistor 2. I can't just go somewhere else. And what's nice about series circuits is that the current is trapped in the loop. So there's no current change anywhere. So the current must be the same through everybody, because every charge carrier that goes through R1 must also go through R2 in the loop. And using our drive-through analogy, if it takes a time R1 at the ordering window and a time R2 at the serving window, it must take R1 plus R2 seconds to get your order. If you have to wait at the first traffic light, then you have to wait at the second traffic light, you have to wait at both. So for series circuits, find REQ, solve for the current, and we use the fact that in series, the current is the same. And then do any analysis you need using Ohm's law, because you'll know the current, so you can just get delta V equals IR for each resistor. So let's do that. We're going to solve these circuits. So always a good first step is to start with our potential diagram. So we have these two resistors. And we start with our high potential. And we actually know what our high potential is. So we'll actually label a value here in a minute. So we've explored. There's not multiple paths. And since this is a complete loop, we know that there's going to be some intermediate color here. So we always define the lowest point of our circuit, our lowest color, to be 0 volts. It's our lowest height. And if what a battery does is it elevates charges, if the EMF is 24 volts, that means that the elevator or the floor, the top floor, must be 24 floors higher than the bottom one. So this potential would be at 24 volts. So that means we're going to have some third potential, some third height that can be anywhere from 0 to 24. And of course, we're going to find what it is, and we can maybe guess. And it'll relate to these resistances. Okay. In our drive-through analogy, the actual battery voltage represents sort of the time, the total time that the loop will be open for, or the amount of time total it could take for a customer. So we'll begin. It says step 1 is find REQ. So REQ for this circuit is really easy because it's in series. Because in series, if I gotta wait 2 minutes, then I gotta wait 6 minutes right after, I've waited 8 minutes. So REQ is just gonna be 2 ohm plus 6 ohm, which is equal to 8 ohm. Okay, so that has reduced the circuit to this. It should be noted that we have created a resistor that just is not real. This is not a real resistor, it just helps us problem solve. And why it helps us problem solve is because now we just have a simple circuit, so we can do Ohm's law. Because if we color-coded our new circuit, we see that it's just all 24 volts are dropped over our fictitious 8 ohm resistor, but we can use the fact that this is always why we do REQ, because we can write the equation I total equals battery EMF divided by REQ. So that's just going to be 24 volts divided by 8 ohms. And remember, an ohm is a volt per amp, so we get 3 amps. And that unlocks literally everything. That unlocks literally everything about our circuit. Because in series, everybody has the same current. So we solved and said that there were 8 ohms of resistance in our circuit. The battery voltage was 24 volts. And we could find our current by using I total equals EMF over REQ. And we found 3 amps. So what is our battery power input? Well, pick your favorite power formula. We know everything now. So power, I might say just use power equals I delta V, because I don't feel like squaring in my head. If you know all 3, please just use I delta V, because it's no squaring. So I is 3, delta V is 24, because we're just talking about the battery. So I get 72 watts. So 72 joules of energy are being transferred from the battery every second. Now we can do our voltage drops. And here's where we start marking up the circuit. So as you find things out, like voltages and currents, please write them in. So we have discovered there are 3 amps of current in this circuit. So that means that coming out of the battery, there are 3 amps of currents. And there's nowhere for these 3 amps to go. It has to hit all the resistors. So the current will hit both resistors. So if we want to find this voltage drop, we use the fact that delta V is equal to IR. The current is 3 amps. The resistance is 2 ohms, so you are 6 volts. So this means we drop 6 volts across the 2 ohm resistor. Now for the 6 ohm, it's the same idea. 3 amps, except now the resistance is 6 ohms, so we get 18 volts. And now we can actually find our intermediate potential, because we said that we start at 24 volts, but we just dropped 6. 24 minus 6, that actually gets us to 18 volts. That's interesting. That's also what we got for the drop across the 6 ohm. And that should make sense if we work backwards. Because if I'm at 0 volts and I go up, I would gain 18. So if I go 18 higher than 0, I get to 18. So you should be able to check by going forwards and backwards. So now we can fill in. So the current through was 3 amps for both. And it actually is worth saying as a note up here that this is the same. So what is the voltage drop? Well, the voltage drop is just delta V equals IR. And the power we can get with I delta V. So voltage drop, 3 times 2 was 6. And 3 times 6 was 18. And the power dissipated, 6 times 3 is 18 again. And 18 times 3 is 54. And notice we actually show conservation of energy, because here, if we check energy conservation, notice that 18 plus 54 is equal to 72. So the total 72 joules per second being transported in by the battery is being burned by the 2 resistors. And notice they're not equal. And this should make sense, because if we go up, we see that there is a larger voltage drop across this larger resistance in series. And that should make sense, because if you think about a customer, if a customer goes down this path, they're going to spend less time in this ordering lane as they do in the picking up their food lane, because there is a longer time required to serve them. And this voltage can be thought of as like the total number of minutes customers would spend in these lanes. So it does make sense. All right, now we'll do a symbol question. 3 resistors are connected in series. The voltage drops are delta VR, delta V3R, and delta V6R. So of course we can do our potential model here. And notice we actually need more colors than we've seen so far. So we know that our high potential is going to be epsilon, because our low potential is 0. So we're going to have some intermediate values too. First thing we want to do is rank the voltage drops and justify without doing math. Then of course we'll do it. So think about this as our car is driving down a single road with 3 stoplights. This one stops your car for a time 1. This stops your car for a time 3. And this stops your car for a time 6. So it makes sense that the time required is going to be the least here, then you spend longer, stopped here, then you spend longer, stopped here. Now, to make that a physics analogy, so we do know the ranking is going to be the lowest voltage drop is across the R resistor, then the next lowest is the 3R, then the next lowest is the 6R. Now, justifying this using physics principles, we know that delta V is equal to IR. And in series, I is the same. So it makes sense that if you're in a series loop with the same current everywhere, the bigger resistances must drop more of the volts. Resistors in series receive the same current. This is a fact. Please remember this. This is a very important fact. Since voltage drop is proportional to current via Ohm's law, and the currents are the same, the voltage drop will be greater for larger resistances. Of course, I tried to conceptualize it a bit with my analogy, but it is essentially just delta V equals IR. I is the same. Now let's do it. So we said that when analyzing series circuits, we want to find REQ. So REQ is quite simple, right? REQ is just going to be R plus 3R plus 6R, which is a conveniently nice number, 10R. Okay. Still not super helpful yet, but why do we find REQ? Because REQ unlocks the battery current, which is the same through all resistors. So our total current is just going to be 1/10 times the quantity epsilon over R. All right, we've learned something new. Let's put it in our circuit. You are 1/10 epsilon over R. Okay. As our current. So let's do it. Delta V across the R resistor is just going to be the current through the circuit times R. Current through the circuit was 1/10 epsilon over R. R is R. So that's going to be 1/10. The R cancels, so we just get 1/10 epsilon. We can probably guess where the other two are going to go, because now we got delta V across the 3R, which is I total times 3R, which is equal to 1/10 epsilon over R times 3R. R goes away again, get a 3 on the numerator, and get 3/10 epsilon. All right, you'll hardly believe what the last one is going to be. Delta V across the 6R is I total times 6R, which is 1/10 epsilon over R times 6R, which is 6/10 epsilon. I'm not simplifying the fraction because I think it shows something here. So notice that we have least and greatest. As expected, the lowest resistance was the lowest voltage drop. The highest resistance was the highest voltage drop. And we can actually fill in our potential values up here, because we said we dropped 1/10 across the first resistor. So this is actually 9/10 epsilon. Then we dropped 3/10. And then we dropped 6/10. So it does work. Goes both ways. So it's always nice when that happens. Now for parallel. So parallel doesn't actually add directly. Parallel adds via what I've been calling the reciprocal rule. And this is also not super helpful. You'll see that it looks like this, but instead, we just, for typing this in our calculator, we'll usually just write this as R parallel equals 1 over R1 plus 1 over R2 to the -1 power, because that undoes this reciprocal. And also, if you only have two resistors, there's a shortcut that you get by writing this as a common denominator, and you'll see that you can do product on top and sum on the bottom. But that only works for two resistors, so I don't really talk about it. And this is actually always less. This is actually always less than any of the inputs. So in series, you're adding the resistances, so it makes sense that R goes up. But in parallel, the more R's you add in parallel, the lower your resistance gets, which should make sense based on our drive-through analogy. Because if R represents the time on average it would take for a customer to get served or pop out the other end of the drive-through, if you add more drive-through lanes, you're serving more customers per second. There's still going to be customers served down the original lane, but if you keep adding more, you keep adding more customers per second, or you keep adding more current to your circuit. So for the same voltage input, you get more current output. So resistance goes down as you keep adding more Rs. So for parallel, it's not actually the current that's the same, it's the voltage drop. And this becomes really clear with the color model, because whenever you color a parallel circuit, you'll see that there's always the same forced color change across the resistors. It's not always red to blue if there's other things in your circuit, but they always have the same voltage drop. So the currents will be different, which should make sense, because if you have a slow worker versus a fast worker, yeah, the lanes are going to be open for the same amount of time, but the slow lane is going to serve a lot less customers. So let's do it. So this is going to mirror what we did last time. So again, our potential explores all our paths until we hit boundaries. Low potential, 0 volts. Battery EMF steps us up to 24 volts. So we actually don't need any REQ business here. Because if we're just asked to analyze this circuit, well, it should be pretty clear to us right now that I dropped the full battery voltage across both resistances. Because I go from red to blue. So I drop the whole thing across both. Because my drive-through's open for 24 minutes. And both lanes are operational for the full 24 minutes. So what's not the same is the current, right? We're going to serve a different number of customers. This is the slow lane. This is the fast lane. So what is voltage drop across each? 24 volts. How do I find current? Well, Ohm's law says current is delta V over R. So 24 over 12, 2 amps. 24 over 6, 4 amps. Power dissipated. Power is I delta V. So you are 48 watts and you are, I believe, 96 watts. Okay. So again, we learned some things. We learned that the current in the 12 ohm is 2 amps and the current in the 6 ohm is 4 amps. And that is an expected result because we said you are the fast lane. So the fast lane will serve 4 customers in its operation time, whereas the slow lane will only serve 2 in the same service time of 24 minutes. So if it takes 24 minutes, if it's open for 24 minutes, you serve a customer every 12 minutes, you serve a customer every 6. Makes sense that you can only serve 2 and the fast lane serves 4. All right. So battery voltage was 24 volts. We knew that. So what is REQ? Well, in parallel, REQ is equal to the sum of the reciprocals, and then you reciprocate that. And if you want to do a shortcut, without typing this into your calculator, a shortcut says that for 2 resistors in parallel, you can, after doing a common denominator, you'll find that it can be written as the product of the resistances over the sum. So this would be 12 times 6 divided by 18. And at this point, I would have just used a calculator because I would have written 18 probably is 12 times 3. So I get 2 ohms. Again, please just use a calculator. Wait, that's just not true. 12 times 3, I'm at 6 times 3. So we get 4 ohms. See, this is why we use calculators. Yeah, so it's 4 ohms. Battery current, business as usual. I total equals battery EMF divided by REQ. So 24 volts divided by 4 ohms gets us 6 amps. And what would the power input be? Well, the power input is, of course, I delta V. Really going to challenge me here. Let's see. 6 times 24. 120 plus 24. 144. Let's check. Is that equal to these two added? I sure hope it is. 48 plus 96 is equal to, that's 14 and 130. So yeah, 144. Nice. So this does work out. Now there is a little interesting thing that happened here. The battery current was 6 amps. Can you see how we got 6 amps and we didn't actually need to use REQ? Well, yeah. If 2 customers got served in the slow lane and 4 got served in the fast lane, 6 got served in total. So this is something known as the junction rule that we'll look at next time. All right. Symbolic version now. 3 resistors are connected in parallel to a battery. We have an R, a 3R, and a 6R like before. So instead of putting them in a series loop, we now put them in a parallel loop. So we know that it's the voltage. That's the same. We can just see the color. But we want to actually rank the magnitudes of the current. So this is really easy with the drive-through analogy because we have the slow lane, we have the slow lane, the medium lane, and the fast lane, right? It takes 6 minutes to get your order, 3 minutes to get your order, 1 minute to get your order, and you get to pick a lane. So it makes sense that for any given time interval, the fewest customers go through the slow lane, then more customers go through the medium lane, and the most customers go through the fast lane. But of course, we live in physics land and not the fast food industry. So we have to actually write this out. So current is equal to delta V over R. And we know that since we're in parallel, the delta V is the same. So we can see that since delta V is the same in parallel, the bigger the resistance, the smaller the current to achieve the same voltage drop. This is also a fact. Please remember this. Just like series equals same current, resistance equals, parallel equals same voltage drop. So since you got to make the same IR in each of the 3 cases, if you have a bigger R, you must have a lower I to compensate. And of course, we can explicitly find each current because we know that in each of these cases, our delta V is equal to the battery voltage epsilon, right? Because if we go here, you are at 0 volts and you are at epsilon volts. So our delta V goes from epsilon to 0 across each resistor. So we can see in each of our cases that I through the R resistor is going to be our battery voltage epsilon divided by R. I through the 3R resistor is epsilon divided by 3R, which is 1/3 epsilon over R. And I through the 6R is equal to epsilon over 6R, which is 1/6 epsilon over R. So we see that the fast lane has the highest current, the medium lane has an intermediate current, and the slow lane has the lowest current. As expected. Almost didn't say that. We have to say our as expected. So how do we measure these things? So we have a magical meter that did it in our Ohm's law question, but remember that potential, we really are only talking about differences because it's about a potential energy. So if I actually wanted to measure potential difference between 2 points, think about your height. How do I measure my height? Well, I can't just put a meter stick up to my head. I have to put a meter stick measuring between my head and my feet. So similarly, for a voltmeter that measures volts, you have to measure between the 2 colors you're probing. So if I want to know the potential difference between red and blue, I need to put one probe at a red end and one probe at a blue end. But for current, so that's going to be in parallel because I'm just observing on the side. The color change will be the same. But for current, that one's pretty easy to justify. I want the current through a circuit. Well, if I want the current in a circuit, I actually just need to put it such that it's observing within the loop. So think about up here. If I wanted to get the current in the loop somewhere, I have to put some sort of observer somewhere in that loop to watch. So current is in series, voltage is in parallel. Notice that's exactly consistent with our rules. So this is a good picture to sort of memorize. So also for our equipment, since our ammeter goes in series with whatever we're measuring, that should be a low resistance. We hope it's 0. Because if it's a high resistance, putting in the current meter is going to totally mess up your current. That one's easy to convince people of. You don't want a lot of resistance in your current meter. But actually for the voltmeter, you actually want a huge resistance. We pretend it's infinite. Why? Well, think about what happens if you have a low resistance, which is what we're actually going to do in our last question here. If you have a low resistance, you're going to essentially open up a free drive-through lane. So what we want is these meters to just be doing effectively nothing to change the circuit behavior. So I just want a quiet observer of the current here, and I want a quiet observer of the potential difference here. But if this is a low resistance, well, it's going to steal all the customers. It's going to make a short circuit. So we have to make this to be basically an infinite wall. Like, yeah, you opened up another lane in your circuit, but it's not going to serve anybody. No one's going to go through it if it's a huge wall. So we're going to justify that here. So first, we're going to consider an ammeter wired in series with a resistor and a battery. So what will happen to the measured current in the circuit if the ammeter has a large resistance? Well, that's not going to be very helpful for us because we're trying to get an accurate measurement of current. So if your ammeter has a lot of resistance, then the current will decrease significantly, so your measurement's not correct. Because we know in this circuit, the expected current is going to be epsilon over R. But if you add a huge R in series in the ammeter, it's going to totally throw that off. So why does an ammeter have 0 resistance? Well, you want to ensure that the current in the circuit is not affected by the ammeter. So you make sure it has no resistance. And of course, it's pretty easy to verify that if you have 0 resistance, this works because Req for your circuit is going to be R from the ammeter plus R of the resistor. And if your ammeter has 0 resistance, that's just going to make Req equal to R. So you get no change. Now what about voltmeter? So voltmeter is in parallel with the resistor. Because again, voltage or potential difference is something that must happen between 2 points. So you can't just put it in the loop. You have to observe the 2 colors that are actually changing. So for our voltmeter, it must live in its own world that shares the potential difference or color change. So it lives in parallel. So again, What will happen to the measured voltage if the voltmeter has a small resistance? Well, if it has a small resistance, it's going to steal the current. It's going to steal all the current from your battery, and it's going to skip it if you open a free path back. So the voltmeter branch is going to steal the current. So this is lowering the current in the resistor, and the measured voltage would be inaccurate. Now, it really only matters when there's other things in the circuit instead of just a single resistor, but the same rationale applies. So it's really going to steal your current because you don't want to open up a free drive-through lane. You want to just watch. You want to observe. So why does a voltmeter have infinite resistance? To make the voltmeter ideal, you want no current to flow down the voltmeter branch. So as such, an ideal voltmeter has infinite resistance. And here we'll actually show that claim. So REQ is going to be equal to 1 over R plus 1 over R of the voltmeter to the -1 power. And we said a voltmeter, if it's ideal, should have infinite resistance. Okay, what is 1 over infinity? Well, 1 over infinity is 0. Think about it. If I do 1 divided by 1 trillion, that is a really, really, really small number. So this becomes 0. So I get 1 over R to the -1, which is R, as expected. So that's why we want our voltmeters to have infinite resistance. We don't want any sort of current theft. And again, this is not really an issue in the simple circuit case, but it becomes an issue when there's other circuit elements in the circuit. But notice this is consistent with our rules. We said ammeters, since they're measuring current, should be in series because current is the same in series. Voltmeter should be wired in parallel because in parallel, potential difference is the same. All right. So now we can start to apply some more complicated rules and deal with circuits that are beyond just the basic parallel and series.